In this last section of Chapter 8, we are going to go through two problems where you are given some data and your job is to take the data and create a graph of the sinusoidal function that models the data and then create an equation from that graph. Let's start with this one here. When the arms of a windmill rotate, the tip maps out a circle with a radius of 7 feet. When an arm is pointing down, its tip is 8 feet above the ground. The windmill rotates once every 6 seconds. So if we look at this arm right here of the windmill, here is the tip of the windmill, of the arm. And if we follow this arm, the tip of it, as it rotates around, it creates a circle. Here's what we know. We know that the radius of that circle is 7 feet. And we know that when the arm is pointing down, just like this arm is doing here, that its tip is 8 feet above the ground. So this distance from the ground to the tip of the arm is 8 feet. The windmill rotates once every 6 seconds. That's going to be important. That tells us what the period of the function is, how long it takes to go through one rotation. Okay, so we have taken in what our information is. We've put some of it in the diagram and identified some of the other stuff. Now let's answer the questions. State the maximum and minimum heights of the tip of the arm above the ground. So if we're following the tip of the windmill, again, it starts here. This would be the lowest position. And so since we're measuring from the ground, our minimum distance would be 8 feet. In all the other positions, it is higher above the ground than 8 feet. So there is our minimum height above the ground. As we follow the tip of the arm as it goes around the circle, it's going to be at the maximum height right at the top of the circle. Now, we've drawn the radius here to be 7 feet, but we should recognize that from the center to the top of the circle, that is also 7 feet. So when we're looking at the maximum height of the tip of the arm above the ground, we will take into consideration the distance that the arm is above the ground, plus the first radius there of 7 feet, plus the second radius there of 7 feet. 8 plus 7 plus 7 is 22 feet above the ground. So be really careful when you're calculating the maximum and minimum heights. It's not just coming from the radius or the diameter of the circle. You have to come and put into consideration how high above the ground the object is. Part B, graph the relationship between the time t and the height of the tip of the arm h, starting in the lowest position for 3 rotations. We are going to create a table of values based on what we know. We are comparing the time with the height of the tip of the arm. We are going to start our table of values with this information. We are starting in the lowest position. So when time is equal to 0, the tip of the arm is facing down, which we know is our minimum height of 8 feet. Here's what else we know. We know that the windmill rotates once every 6 seconds. So for it to go all the way around and back to that minimum height again, that takes 6 seconds. So in my table of values, I'm going to skip down a little bit, and I'm going to put at time is equal to 6. We'll be back at that minimum of 8 feet. Well, I need to know some points in between being at the minimum and going all around and getting back to the minimum. So let's talk about some other points that would happen on this graph. If it takes us 6 seconds to go all the way around, how long will it take us to go halfway around? Halfway around the circle is going to take half the amount of time, so it will take us 3 seconds. So at 3 seconds, let's talk about what height we're going to be at. Since we started at the bottom, halfway around the circle would be at the top, which means we are at our maximum height. We established what that maximum height is in A, so we would be at 22 feet at 3 seconds. Now let's talk about 2 other times. What happens, or how long would it take us just to get from the bottom, from the minimum point, to where the center of the circle would be, or equal to the center of the circle? Well, what I notice is that this little green portion here is a quarter of the way around the circle. So if it takes us 6 seconds to go through one rotation, how long will it take us to go through a quarter of a rotation? Well, it's going to take us a quarter of 6 seconds, which would be 1.5. You can also see that even if we look between the 0 and the 3, if it takes us 3 seconds to get halfway around, it takes us 1.5 seconds to get a quarter of the way around. Well, what's our height there? We're not at the maximum. We're not at the minimum. We're at the center. So what we're going to add there is the 8 feet that we are above the ground plus the 7 feet diameter. That would give us 15 feet. So here we're asking for the minimum and the maximum. We might even say, where's the midline? And it would be at 8 plus 7, the minimum height plus the radius. So 15. One more point, and let's talk about what happens if we get to the other side of the circle. So not quite a full rotation, but again, equal with the center. That would be 3/4 of the way around the circle. 3/4 of 6 is 4.5. And you might also just even notice a pattern here that each of these is a difference of 1.5 seconds. So that works too. What is our height? Again, our height is that center of the circle. So 8 feet above the ground plus the 7 feet radius, 15 feet total. There are our coordinates that we are now going to plot on this graph. And these are the points that you can always use. Use your 2 minimum points. Your maximum point will always be right in the middle of your 2 minimum points. And then your 2 midline points will be right in between the minimum and the maximum, and then the maximum and the minimum. Okay, so now we need to label and scale our axes. X is the time, which is in seconds. The height is in feet. Now, for time, we need to go from 0 to 6, but we need to be very, very careful. We want to go through 3 rotations. So I need to go up to at least 18 seconds because each rotation is 6 seconds. We want to go through 3 of them. 3 times 6 is 18. And down here, we can actually, for the time, count by ones. I'm only going to label the 2s, but 1, 2, 3, 4, 6, 8, 10, 12, 14, 16, 18, which gives me plenty of room there. For height, we have to go from 8 feet to 22 feet. And again, I have enough room here where I can just count up by ones. Again, I'm just going to label the 2s. So 1, 2, 3, 4, 5, 6, and so on. 8, 10, 12, 14, 16, 18, 20, and 22 is our maximum. So this grid works out quite well for this one. And there is our scale. So make sure you label it and you number it off. You scale it as well. Okay, let's start to plot some points. So we have the point 0, 8. That's where we start. We're at our minimum point. Then at 1.5, we are at 15 feet. At 3 seconds, we are at our maximum of 22. At 4.5 seconds, back at that midline. And then at 6 seconds, we're back at 8. And again, have a look at your points. It should create a perfect triangle. Now you might be saying, well, how do I keep on going? Because my table of values only goes up to 6. Well, just keep following the pattern. We're always moving over 1.5 seconds, and then we just follow the pattern of these numbers. So we would go to 7.5 seconds and be at 15. And then we would be at 9 seconds. We would be at our maximum. And then at 10.5 at the midline, and at 12 at the minimum. And let's do that one more time. 13.5 at the midline, 15 at our maximum, 16.5 at the minimum, and at 18, we're back there. And again, they should all be perfect triangles. Look at those nice straight lines. When we connect the dots, though, we're not going to connect them with straight lines. We're going to create our sinusoidal curve. Maximum, minimum, maximum, minimum, maximum, minimum. Do the best you can. That was not great, but there we go. And there is our graph of our relationship. This is the tip of the windmill. It's at the bottom. It travels up to the top. It goes down to the bottom again, and it does that again and again. We can label some points on here. Let's just label our first rotation. We have 0, 8, 1.5, and 15. 3 and 22. Just fix that. 3 and 22. 4.5 and 15. And there's 6 and 8. And we could keep labeling if we want. I'm just going to label the first rotation. So there's your points. Okay, next, write the equation. So you'll remember from 8.4 that our parameters represent specific characteristics of the graph. So A represents the amplitude. B comes from the period. It comes from 2 pi divided by the period. D comes from our midline. You'll also remember that we talked about when we have any application questions where an object is moving in a circle like we have here, A, the amplitude, is always the radius. B always comes from the period, so nothing there. D, the midline, when something is moving in a circle, is our center. So when we look for A here, we want to calculate the amplitude. We could go maximum minus the minimum divided by 2. So we could go 22 minus 8 divided by 2 and get the amplitude that way. Or we could simply look at what the radius is. The radius in this question is 7. It was given to us. Our amplitude then, our A value, is going to be 7. We can check it at the formula if we want. 22 minus 8 divided by 2. 22 minus 8 is 14. 14 divided by 2 is 7. But you don't even need to do that calculation. As soon as you know the radius of the circle, that's your amplitude. B value is 2 pi divided by the period. So our period here is 6 seconds. 2 pi over 6 is great, but it can be reduced. It can be written as pi over 3. And in some instances, you could even just put that in your calculator and round it. I'm going to leave it as exact value, but you could put it into your calculator and round it to any number of decimal places. D, the midline, is where the center of the circle is. And we established that. The center of the circle, the center of the windmill, was at 15 feet above the ground. So right away, our midline, our D value, is 15. Could we use the calculation if we wanted to? The formula? Sure. Max plus min divided by 2. 22 plus 8 is 30. divided by 2 is 15. So you can use it as a double check if you want, but you don't even need to do that. The center of the circle is always the midline. Let's go ahead then and write our equation. H equals 7 times the sine of pi over 3, t minus 1.5. So recognize there is a c value there. It's given to us. Finally, plus 15. And there we have our equation. That shows this graph. That represents this data. Now, sometimes in these questions, you might also be asked to maybe take a given t value and find the height, or take a given h value and find the time. You can do that right on your calculator. So enter the function into your calculator into y equals. If you have a given t value, you can use your table to find h. If you're given an h value, put it into y2, find your intersection point to find t. Let's do this again with the next example. The next example is again an object that's moving in a circle. That is a Ferris wheel. We're going to read the question. We're going to label some stuff on the diagram, and then we're going to do the same thing. This Ferris wheel has a diameter of 50 meters and completes a full rotation every 46 seconds. When you first load at the bottom of the wheel, you're on a platform that's 3 meters off the ground. Diameter of 50 meters. So we're going to sketch that diameter in again, and you'll notice we did this on this question too. We often draw, or almost always draw, our radius or our diameter vertically. It just makes it much easier to determine the maximum and minimum heights when we do that. So I'm going to do the same thing in this one here, and I'm going to draw the diameter right here. We know that that is 50 meters. We have a full rotation in 46 seconds. That is the period of the function. How long it takes to go through one rotation is the period. And then it is 3 meters above the ground. So this little tiny distance, this little bit in here, is 3 meters. Part A, state the maximum and minimum heights of a rider above the ground. Again, our minimum height comes from the distance that we are from the ground. So when you get on a ride at the bottom, you're at the very, very bottom, anywhere above. When you're anywhere else on the ride, you're higher than 3 meters. Our minimum height is 3. You take the Ferris wheel, you are going around the Ferris wheel. When you get to the very top of the Ferris wheel, that's the highest you are above the ground. That's your maximum height. In this case, our maximum height takes into consideration the 3 meters above the ground plus our 15-meter diameter. Our maximum height is 53 meters above the ground. Again, be careful. Our maximum and minimum heights are based off how far above the ground we are plus the diameter or the radius of the circle. We're going to talk about this now. We didn't do it in the last one, and I know it doesn't ask for it. Let's talk about where the midline is. Let's talk about where that center of the circle is. So right here, how far above the ground are we with the center of the circle? Well, we know that that 3 meters is going to come into play. What is this distance right here from the first chair up to the center? Well, if our diameter is 50 meters, that means our radius is 25 meters. So our midline would be 3 meters above the ground plus that 25-meter radius. Our midline is at 28 meters. Now, I know this part A didn't ask for that, but we know we're going to need it when we're graphing. So we're just going to talk about it now while we're talking about the max and the min. All right, part B again. Graph the relationship between time and the height of the rider above the ground, starting in the lowest position for 2 rotations. Label at least 5 coordinate points. Well, we're going to label everything, but let's start with our table of values. Again, we are comparing our time, which would be our x coordinate, with our height, which would be our y coordinate. Again, we're starting at time is equal to 0, and we are told we're starting in the lowest position. So we're starting at our minimum. Our minimum height is 3. We know that it takes 46 seconds to go all the way around the Ferris wheel. Takes 46 seconds. So if I start at 3 minutes or at 3 meters, then it's going to take 46 seconds to get back to 3 meters. I'm going to leave a little bit of room and I'm going to put that time and that height there. We've got some times in between. So let's talk about that. If it takes us 46 seconds to go all the way around the circle, how long does it take us to go halfway around the circle? Well, half of 46 is 23. And when we're halfway around the circle, we are up here at the maximum. So that would be at 53. So at 23 seconds, we are at 53 meters. Let's talk about how long it takes us to get to equal or even with the center. So how long does it take us to go from the lowest point to this part right here, which is even with the center? Well, that's a quarter of the way around the circle. So if it takes us 46 seconds to go all the way around the circle, how long does it take us to go a quarter of the way? A quarter of 46 ends up giving us 11.5. You could also think of it as we are halfway in between 0 and 23 seconds because it takes us 23 seconds to get halfway around. So a quarter of the way would be halfway to 23, which is 11.5. What's our height there? Well, we calculated that. Our height at the center is the 28. It's our midline. And then finally, let's talk about how long does it take to go 3/4 of the way around. 3/4 times 46 is 34.5. We can also start to recognize that the difference between each of our points here is 11.5 seconds. So 0 to 11.5, another 11.5 gets us to 23. Another 11.5 is 34.5. Another 11.5 gives us to 46. Okay, and that will always work with sinusoidal functions. There's always going to be an even distance between your minimum and your midline and your maximum and your midline and your minimum. The height here will be at the midline, which is 28. So we've got our table of values. Let's go ahead and let's label our axes. Again, time is our x, and that is in seconds. And this is going to be our height, h, which is in meters. Okay, now, admittedly, this grid does not work great for these numbers, but we're going to make it work. Now, we want to do 2 rotations. So 46 seconds is 1 rotation. We're going to have to go up to about 92 seconds so that we can get 2 rotations in. Now, there's not a whole lot of lines here. So what I'm going to do is I'm going to count up by 3s. I'm just going to do the best I can. And again, I know that 3s doesn't work great for these times either, but it's really the best I have right now to fit on this grid. So this is going to be 3 seconds, and then I'm just going to keep counting up by 3s all the way. I'm going to actually skip the in-between ones. Okay, so 3, 9, and then we'll just keep going. Okay, that'll be 18. 21, and then 24, and we'll keep going. 27 and 33. 39, 42, 45, 48, and then 51, 54, 57. Just keep going, counting up by 3s. Okay. And then sorry, so we're going to go 63, and then 66, and then 69, and 72, and 75, 78, and 81, 84, and 87, and then 90. We can't quite fit it, but we know 92 will be over there. Okay, and then our height, which is measured in meters, we have to go from 3 all the way up to 53. Again, not the ideal grid here. I'm going to go up by 5s, which again, not perfect, but it's what we have. So we're going to work with what we have. So this will be 5, and then I'm going to skip 10, 15, 25, 35, 45, 55 meters. So there we have that there. Okay, so we are going to have to estimate where some of our points are, but that should be okay. So at 0, we're at 3. So I'm just going to put that below the 5 there at 3. At 11.5, so 9, in between, this is be 12 right here. So we're going to kind of snuggle a little bit close to that, and then we're all the way up at 28. So this is 30, so somewhere in here, and it's okay to estimate where it's at. Then at 23, so here's 21, here's 24. So right in here, we're up at the top at 53. So not quite at that 55. We'll be about there. 34.5. So here's 33 and 36. So right in the middle there, we'll be back at that midline. And then at 46, we're back at 3. So snuggle that right in there. And again, they're kind of these estimated points, but you can see, look at that nice triangle that is created there. Okay, now, again, we don't have a number of table of values, but we're going to keep going. Our next point would be 11.5 again away, which will be at 57.5. Okay, so here is 51. And a bit over from there. So there we go. There, back at the midline. And then we are at 69 and our maximum. And then we're going to be at 80.5 and our midline. And then at 92 and our minimum. And again, look at that, a perfect triangle. That's maybe a little bit high there. Okay, connect the dots with your sinusoidal curve, minimum, maximum, minimum, maximum, and back to minimum again. Kind of missed that point there. And there is your sinusoidal curve. So even if your points are not, or your grid doesn't match the greatest and you have to estimate, that's fine. It's still going to create a nice sinusoidal curve for you. It's going to sketch that in a little bit better. So I'm actually touching all of the points. Here we go. There, that's a little bit better. Good. Okay, I'm going to label in a couple of those points for you. So from the first one was at 0.3, and then 11.5 and 28, 23, 53, 34.5 and 28, down here at 46 and 3. This was 57.5 and 28 at that midline. This was at 69 and 53. And then this was at 80.5 and 28. And then down minimum at 92 and 3. So those are all the points that we created. Okay. Part C, write an equation again. So now we're taking those characteristics and putting them into the sinusoidal function form. A, again, is our amplitude. Again, because we have an item that is moving in a circle, the amplitude is the radius. We were given the diameter of this Ferris wheel, so we could easily find the radius. It would just be half the diameter. We also established the diameter when we were talking about the midline, or the radius, sorry, when we were talking about the midline. So that would be 25. So we don't even need to do any work there. The amplitude is equal to the radius. The radius is 25. The B value comes from the period. Our period is 46, so 2 pi over 46, which reduces to pi over 23. We can leave it as exact value as pi over 23. You can also put pi over 23 in your calculator and round it. The D value is our midline. When we have something that moves in the circle, the D value comes from the center of the circle. Again, we talked about it. We talked about it up here again. Okay, the center of the circle, radius plus that minimum height there. So 28 is our midline. Our equation then is h equals 25 times the sine pi over 23, times t. Again, we have that c value there. Don't worry about it. Just write it down. Plus 28. And there is your equation that models this function, that models this data. We could take this equation now and graph it in our calculator. We could take a given t value and find an h value by using the table. We could take a given h value and put it into y2 and find the intersection point to find the t value. But for now, we're content with just writing the equation.